Okay. All right. So welcome everyone. It's great to have so many attendees today. We're really excited with this series of presentation. Without further transition, I will just say a couple of words about this webinar series, why we do this, and introduce our first speaker. So yeah, NMR, we're a company who use photo kidnap for direct design. And we have our own bias about photo kidnap, using it for the pharma industry, but we're really excited about all the applications that are being developed. And we thought it would be great to have, the bright mind, people who are active in the field or pushing the boundaries of this field. And yeah, we had great response from the community. We're really happy to have such great speakers today. So the first speaker that we have is Alexey Kiryutin, who is a researcher at the tomography center in Novosibirsk, and he's been doing his PhD in Novosibirsk. He's been as well with Hans Martin Witt in Berlin and in Darmstadt, working on photo kidnap, and is also known for having developed and invented the field cycling photo kidnap. This is particularly useful for G factors in my experience. So great to have you here. Today is going to talk to us about Photo-SABRE. I don't exactly know what it means yet, but I'm really excited to discover what you have to show us, Alexey. And yeah, the floor is yours.
Yeah, thank you. Let me share my screen. Is it okay? I see.
Very well. Thank you.
So sound is fine, yeah?
Yes.
Okay. Good afternoon, colleagues. I would like to thank the organizers and Felix Torres for inviting me to speak at the seminar on light application in NMR. It's a great pleasure to present our recent results as an opening talk. This is our tomography center. It was found jointly with a Bruker in 1989, and I'm working here since was student starting from 2002. While this seminar is about NMR and its modern uses, it is worth noting how versatile the method is, from chemistry and pharmaceuticals to food science and MRI. Still, NMR has one major drawback: low sensitivity. The low sensitivity of NMR stems from the extremely weak interaction of nuclear spins with the external magnetic field. As a result, we have tiny energy splitting between levels of spin states alpha and beta, and consequently very low thermal spin polarization. At standard conditions, like a room temperature and magnetic field about 10 Tesla, we have only 0.01% of polarization. By NMR, we detect only difference between energy levels, populations. On the right-hand side, you see the case of hyperpolarization, in which all of nuclear spins have a single alpha projection. This leads to huge signal in NMR. In this case, we have an enhancement factor of 10,000. While several methods exist to enhance NMR sensitivity, including light-induced approaches, our work utilizes a parahydrogen as a source of hyperpolarization. A parahydrogen represents a spin isomer of hydrogen molecule where the proton spins are antiparallel, forming a singlet state, with a configuration makes the molecule non-magnetic and unresponsive to external magnetic field. The separation between ortho and parahydrogen is possible due to the different rotation quantum numbers achieved through simple cooling in the presence of the conversion catalyst. Here we show typical parahydrogen enrichment levels. At liquid nitrogen, we obtain about 50% of parahydrogen, while at 22 Kelvin, we achieve over 99% of parahydrogen. In our experiments, we worked with a parahydrogen enriched below or above 98%. This makes parahydrogen an inexpensive and very powerful source of spin order that can be stored in a pure form for several days without significant losses. This slide illustrates the key process of transferring the singlet spin order from parahydrogen to nitrogen nuclei in azobenzene or other substrate. The method called SABRE, signal amplification by reversible exchange. It was discovered in 2009, not so long ago. The heart of a SABRE is an iridium-based complex that plays a dual role. It makes possible the reversible binding of hydrogen molecules on one side, while simultaneously coordinates substrate with a nitrogen on the other side. The chemical part of SABRE depends on many parameters, including concentrations, para-hydrogen pressure, temperature, and reaction rates. However, the physical component is equally crucial. Without proper magnetic field and scalar spin-spin couplings between the hydrides and the substrate nitrogen, the polarization transfer cannot occur. Optimal magnetic field strength varies significantly depending on the target nuclei. For efficient heteronuclear polarization transfer, for example, nitrogen, the best field is slightly below 1 microtesla, but for proton polarization, much higher field is required, which is 5 to 10 millitesla. The advantage of this method is that with continuous para-hydrogen flow by bubbling solution, for example, in the optimal magnetic field, we can achieve persistent substrate polarization. To understand the efficient polarization transfer, let's look at a simple free spin system consisting of 2 hydride protons and 1 nitrogen spin of bound substrate. When we calculate and plot the energy levels versus magnetic field, we observed that at very low field, 2 levels should theoretically cross. However, due to non-zero spin-spin coupling, these levels undergo an avoided crossing, which is called a level anti-crossing or simply lag. The position of lag depends on all spin-spin couplings in the system and gyromagnetic ratios of both hydrogen and protons, hydrogen and nitrogen. In the simplest case, where proton-proton coupling dominates, lag occurs at several hundred nanotesla, which is 100 times lower than the Earth's magnetic field. Let's consider a system initially prepared in the proton singlet state. During adiabatic magnetic field variation, we selectively populate only beta states of the X nucleus. This creates a hyperpolarized substrate that subsequently dissociates from the complex and goes to the bulk. Remarkably, when we perform experiment exactly at the lag position, we observe an analogous effect. One spin projection of the X nucleus will be populated through the same mechanism. It is important to mention the fundamental work of Konstantin Ivanov, who received at 2020 the Günther Lauken Prize for the elucidation of the SABRE mechanism shared with the Simon Duckett and Warren Warren. We remember Kostya. His brilliant career was tragically ended because of COVID. This slide presents the growing list of the molecules that can be hyperpolarized using a SABRE method. In recent years, researchers have achieved significant results with the pyruvate ion, a crucial metabolite used in cancer diagnostics via carbon-15 MRI. A SABRE method is advancing rapidly. New target molecules for SABRE are being discovered each year. Chemists develop new polarization transfer complex, including water-soluble iridium-based catalysts. And we now turn to the focus of our study, azobenzene. This remarkable molecular photoswitch exists in a thermodynamically stable trans isomer that undergoes reversible light-induced transformation. UV light converts trans to cis isomer, but visible light or thermal relaxation drives cis back to trans isomer. On this slide, I listed several applications, including light-controlled structural modulation and even solar energy storage. Azobenzene has become the gold standard photoswitch. Anytime we need precise reversible light-driven molecular changes, we better choose azobenzene. Concerning our topic, I tell you some facts about 15N enriched azobenzene. Trans-azobenzene is planar and cannot be directly polarized via SABRE mechanism due to steric hindrance at the iridium complex, while cis-azobenzene coordinates easily, yielding strong 15N polarization, which was published before. Both isomers show similar longitudinal relaxation, about 4 to 5 minutes at low fields and several seconds at high field due to strong chemical shift anisotropy relaxation mechanisms. The game-changing discovery was done by Kirill Shebersov in our group being in Novosibirsk. He found that trans-azobenzene exhibits record long-lived spin states, almost 20 minutes lifetime and a dual spin locking at high fields. Such long-lived spin states can exist only in magnetically equivalent nuclei with high symmetry in a rigid molecules. By the way, parahydrogen is the simplest case, which can live for many days. LLS in cis isomer lives only several seconds, just slightly longer than T1. This phenomenon of long-lived states, well developed by Malcolm Levitt group and his group in Southampton, it actually opened new horizons. When we realized these facts 4 years ago, our mission became clear: to hyperpolarize trans-azobenzene by SABRE and lock its polarization for 20 minutes in his long-lived states. We came to the idea of Photo-SABRE. Our goal was to combine all our existing capabilities while solving several critical technical problems simultaneously. First, we needed to introduce light into the magnetic field without distorting the ultra-low field environment. Even a minor disturbance would ruin the polarization transfer. Second, the system had to maintain high-pressure parahydrogen delivery up to 10 bars, while accommodating this optical setup. And crucially, we had to preserve sub-Hertz NMR resolution despite the sample shuttling rapidly between fields. I'll be honest, this was an incredibly exciting challenge. The difficulty of getting everything to work together: light illumination, parahydrogen bubbling, sample shuttling, field cycling in the magnetic field, and NMR detection with long-lived state option. To perform SABRE, a measurement in arbitrary magnetic fields, we already had a setup based on moving the sample along the axis of the cryomagnet, which I constructed in 2016. This setup allows us to vary magnetic field from 2 millitesla to 9 Tesla by positioning the sample. At the top of the cryomagnet, a magnetic shield is installed with internal electromagnets, enabling the variation of magnetic field from 10 nanotesla to few millitesla. Thus, we cover 9 orders of magnitude in a magnetic field strength. A special adapter for screw cap NMR tube equipped with a Teflon tubes allows us to bubble the solution under pressures up to 10 bars. The gas system enables sequential delivery of 3 different gases. From the NMR side, we can use standard TXI and BBO probes while keeping high resolution and reproducibility. The setup is highly robust. Since it starts, it has performed over 2 million sample movements. The video clip demonstrates real-time sample movement, which is sufficiently for the majority of experiments. The whole setup is controlled by the PC computer directly from TopSpin Pulse program. By the way, the similar setup I have built in Darmstadt in Gerd Bunkowski group in Germany, and copy of it was constructed in University of Southampton in a Malcolm Levitt group. To irradiate the sample inside the magnetic field, I initially used a simple LED of various wavelengths arranged around the perimeter of the guiding tube to illuminate the sample from all sides. From the perspective of illumination, this setup worked well. However, there was a problem with the magnetic field. It turned out that LED was slightly magnetic, but more important, the current flowing through them produce additional magnetic field, which significantly disturbs the ultra-low magnetic field, which was unacceptable for our experiment. So I decided to place the light source outside the magnetic field and deliver light using 2 mirrored surfaces, as it is done in the periscope. This approach required the use of small diode lasers with a non-divergent beams. Examples of such inserts are shown on the slide. At the first stage, I used 5 lasers, but in the final setup shown here, I used 7 high-power diode lasers with a wavelength of 450 nanometers to produce more light power. The total electrical power is 9 watts, and the optical output reaches 1.2 watts. Aluminum heat sinks you see with the small fans were used to dissipate heat from the lasers, but to cool the sample exposed to the intense light, we used air channels inside the walls of this tube. This design turned out to be very successful. It is easy to install in our existing magnetic shield and allows for highly efficient sample irradiation. I have to say that all of this became possible due to 3D printing. The updated design could be fabricated within a single day without even leaving the lab. The slide shows a series of proton NMR spectra of azobenzene recorded after continuous green light irradiation every 3 seconds. One can clearly see the gradual transformation of trans-azobenzene into the cis isomer. On the right, photoisomerization curves are shown for different concentration of azobenzene. The higher the concentration, the slower the photoisomerization proceeds, which is explained by the increased optical density. These initial experiments demonstrated the importance of delivering as much light as possible to the sample in order to be fast to convert trans to cis and cis to trans. So we applied the protocol shown on the right. We irradiated a prepared solution containing a mixture of cis and trans azobenzene and activated iridium complex in an ultra-low magnetic field while simultaneously bubbling parahydrogen through it. First, we looked at the proton NMR spectra. It turned out that without light, only the cis azobenzene is polarized, whereas under light, both isomers become polarized. We then repeated the measurement for 15N and even for carbon nuclei. In this way, we converted our dreams into reality. Continuous light irradiation simultaneously converts cis to trans and trans to cis, allowing us to polarize trans-azobenzene. In other words, light activates the chemical exchange between the two isomers. The molecular photoisomerization proceeds very rapidly, so the spin polarization is not lost during the transition. To measure the magnetic field dependence of polarization transfer, we conducted a series of experiments in which the field inside the magnetic shield was varied. We found optimal magnetic fields for different types of nuclei, but most importantly, we confirmed that the field dependence profiles for cis and trans azobenzene are identical, differing only in amplitude. I won't go into details about the field dependence here, but I want to mention that for 15N nuclei, the optimal magnetic field is around half of microtesla. This table shows the maximum enhancement factors and polarization levels achieved under optimal conditions. As it is seen, the polarization on nitrogen nuclei reaches 7.5% for cis isomer and 3% for trans azobenzene, which is very good results. I'd like to point out that in such a system, achieving the highest enhancement factors requires additional experimentation. For instance, the concentration of azobenzene is a key parameter. It affects both the optical density and the exchange rate with the iridium complex. I suspect that this system can be tuned and polarized even stronger. We also performed experiments varying the irradiation and bubbling times, the so-called build-up curve. It shows how the polarization on trans-azobenzene slow increases all the time. In this case, the rate of photoisomerization on the entire sample volume plays a crucial role, and also mixing of the sample plays a crucial role. We also carried out a relaxation experiment in the dark. This showed that in ultra-low magnetic fields and in the Earth's field, 50 microtesla, cis azobenzene relaxes very rapidly in the presence of the iridium complex, while trans azobenzene exhibits a T1 relaxation time about 100 or 200 seconds. The SABRE experiments with azobenzene were highly reproducible, and the sample showed virtually no degradation, which allowed us to perform relaxation measurement in a magnetic field range from 1 millitesla to 9 tesla. The protocol of this experiment is shown on this slide. The so-called relaxation dispersion, or T1 dependence on a magnetic field, for the two azobenzene isomers is shown on the slide. When compared to the data obtained by Kiryutin source for the azobenzene, thermal azobenzene in acetonitrile, we see the T1 behavior of the trans isomer remains unchanged. In contrast, the cis isomer shows significantly faster relaxation in magnetic field below 100 millitesla. This can be explained by chemical binding to the bulky iridium complex, where the relaxation time is evidently shorter. The sharp drop in the strong magnetic fields is attributed to the chemical shift anisotropy mechanism, and the quadratic increase in relaxation rate with the field strength has been observed. The final part of my talk concerns long-lived spin states. As I mentioned earlier, LLS can exist in a system with high symmetry, with a spin 1/2 pairs, or in system of A prime, M prime kind. There are pulse sequences designed for the detection of long-lived spin states. Two examples are shown here. For example, S2M pulse sequence and slick spin lock-induced crossing. We tested both approach and found that the S2M sequence works better for the case where the chemical shift is slightly changes due to, for example, temperature variation. The spectra show how the 15N signal of polarized trans-azobenzene looks like when we detect with a slick pulse sequence. A doublet is observed, which is expected compared to the conventional magnetization-based detection. It was interesting to investigate the magnetic field at which Photo-SABRE is most effectively in populating long-lived states. It turned out that zero magnetic field is the most efficient. The small dip here in the center is an artifact of the experimental setup near zero field. Residual transverse field component of about 30 to 50 nanotesla remains, which can significantly affect measurement in this range. The last slide shows the spectra of trans-azobenzene and the relaxation kinetics in logarithmic scale for magnetization at 9 Tesla, at 0.1 Tesla, as well as the decay kinetics of long-lived spin order in high field under double RF spin lock. It is clear seen that the LLS signal persists even after 17 minutes, while the magnetization has completely decayed. On the right side, proton NMR spectra of the long-lived spin order of the orthoprotons are shown. Fitting the data allowed us to determine the relaxation times of the combined multinuclear 1H and 15N long-lived spin order, which is 1,200 and here 1,000, almost 500 seconds, corresponding to 20 and 25 minutes, respectively. So in conclusions, for the first time, we have successfully hyperpolarized trans-azobenzene using Photo-SABRE method under light radiation, achieving a 15N signal enhancement more than 9,000, which is 3%. Polarization is transferred from the cis isomer, which is directly polarized via SABRE at ultra-low magnetic fields. The long-lived spin order of trans-azobenzene populated directly during SABRE at near zero field exhibits a remarkable lifetime of 25 minutes, far exceeding its T1 relaxation time at high field. This multinuclear spin order can be detected via both 15N and proton NMR. This work bridges photochemistry and hyperpolarization, enabling new application for light-responsive system in MRI and NMR. So results are published in this paper. And the last slide, here is our team with whom I was working in Novosibirsk. I'm thankful to all of them, but here I highlighted who are involved in this work. So thank you for your kind attention.
Thank you, Alexey. Thank you so much. It was an amazing presentation. Beautiful science. And I think, do we have any questions already in the Q&A in the chat? Yes, I see a question from.
Okay.
I find the questions. Don't worry. So we have a question from Ron Lawler, Professor Ron Lawler, who asks, have you considered using substituted azobenzenes?
Actually not. So you see, we used a doubly labeled 15N azobenzene, which we got from Herbert Zimmermann, And we tried to use other benzene water soluble, but they are not 15 labeled. So we tried only at natural abundance, but with natural abundance, first of all, signal is tiny, but also we found out that N14 causes relaxation very fast. So actually we tried, but we would like to have 15N labeled substituted as a benzene. It's interesting topic. Yeah.
This makes sense. We have a question from Sadam Adebayo. Thank you for the good work. My question is, does this signal enhancement help in the acquisition of 2D NMR spectra?
Oh, yeah. Yeah, sure. It's possible to, I think I have even done a 2D experiment with the hyperpolarized azobenzene. I think it was kind of noisy or XE experiments. Yeah, sure. Within single scan, you can acquire one transient, and then the important thing that it should be reproducible, but our setup actually quite reproducible, and every transient could be started with the same, almost with the same amount of polarization. Yeah, it's possible.
Maybe I have a follow-up question for you, because one thing that I remember from 2D's hyperpolarization is often we can use gradients, for instance, to measure a 2D within one scan. And because one challenge is often to recycle the hyperpolarization from scan to scan. So we tend to either do that or do small angle excitation, so that we can record 2D. We can keep some polarization in the Z axis. And in photo-kidnap, for instance, you can simply recycle polarization, the limit of bleaching by pulsing again light and light. Is that possible with the field cycling and the para-hydrogen bubbling? Would you be able to do that with your system, to just bring the sample up and down?
Possible. So the SABRE is a very nice method actually. So it's quite reversible. So you can produce your hyperpolarized signal just in 1 day or even 2 days, just bubbling and measure bubbling. What you need to take care, about evaporation of the solvent. But this, if you bubble a lot with a dry hydrogen, you can evaporate your solution or solvent. But this can be solved by pre-moisturing, so to say. So, in gas phase, you can add vapors of your solvents, and then you can bubble for several days. And for some system, it's reproducible. For some, of course, not. But it's, as I remember, since I did Kidnap is really fast degrading system. Usually you cannot do 1 hour illumination. It will deplete
oh, no.
it. Yeah.
Absolutely. I will finish maybe with a last question, which is a follow-up question from Sadam Adebayo, which is there any constraint of temperature for maintaining the long-lived state?
Temperature. Well, I think since it's in a liquid state and you don't have any kind of phase transition, meaning crystallization, it should be fine. So we actually didn't change so much temperature, did not vary. But I think if it's in a liquid in the same, let's say, phase, I don't think that temperature will change a lot. Yeah.
Excellent. Thanks a lot. Yeah, I think we are in time to move to the next speaker. Thanks a lot, okay. Alexey. Again, very interesting. I can see a lot of potential applications going down to MRI eventually one day. So that's yeah, that's where it starts. Really, really nice. Thanks a lot.
Thank you.
And with that, I will start to introduce our next speaker, who is Lars Kuhn, Dr. Lars Kuhn, who is